Ever look at a massive, really complex machine like a hybrid cement mixer and just wonder, how in the world does that actually work? Well, it's not just about the heavy metal, it's about building a brain. And today, we're going to dive deep into the engineering blueprint for that very brain, the Supervisory Controller Unit. Let's get into it. So here's the game plan. First, we'll get a handle on just how complex this machine is. Then, we'll check out the super clever blueprint for its brain. After that, we'll see how engineers bake safety in from the very beginning, put the whole thing through an insane stress test, and finally, we'll wrap up with why this whole process is so incredibly important. All right, let's start with the big challenge. How do you possibly control a machine that's part combustion engine, part high-voltage electric powerhouse, and part heavy-duty industrial equipment, all at the same time? I mean, just think about it for a second. You've got a diesel engine, a huge 400-volt battery, a powerful electric motor, and, of course, that giant rotating drum. All of these different parts have to be in constant communication, right? They're sharing power and data every single millisecond, whether the truck's barreling down the highway or mixing concrete on a job site. And that, right there, that is the central question for the engineering team. Because the failure here isn't just some error message on a screen. It could mean a stalled truck in the middle of traffic, damaged equipment, or way, way worse, a serious safety incident. The answer, the solution, is the Supervisory Controller Unit, or SCU. This is the brain of the operation. It's the conductor of this incredibly complex orchestra. It's taking in signals from tons of sensors, getting commands from the driver, and it's making thousands of decisions every single second to keep the whole show running in perfect harmony. So how do you design a brain that's not only smart, but also unbelievably reliable? Well, you start with a really brilliant architectural blueprint. The secret sauce really is separation. You basically build a digital wall right down the middle of the software. This creates two totally separate, isolated partitions that have very, very different jobs. And this design ensures that no matter what goes wrong, the system can always fail in a safe way. And you can see that separation right here in this architecture diagram. Up top, you've got the safety partition, and below it, the functional partition. Now notice how every command from the functional side has to pass through that central choke point, that torque and direction safety arbitration layer. That's a bottleneck on purpose, and it's controlled by the safety partition. Safety always gets the final vote. You know, a great way to think about this is like having a guardian and a worker. The safety partition, that's the guardian. It doesn't care about how fast the drum is spinning, only that it's spinning safely. Its one and only job is to watch for danger and prevent disaster. Then you have the functional partition, and that's the worker. It handles all the day-to-day stuff, managing the battery, responding to the remote control, setting the drum speed. The worker gets the job done, but the guardian is always watching over its shoulder, ready to step in at a moment's notice. Okay, so having a great architecture is a fantastic start, but how do you actually prove that it's safe? Well, you don't guess. You follow a strict, internationally recognized process. In the world of cars and heavy machinery, there's a thing called ISO 26262, and it is the absolute gold standard for functional safety. It's not a suggestion. It's a formal rulebook that forces engineers to think about everything that could possibly go wrong at every single step of the process. It's all about building safety in, not just bolting it on at the end and hoping for the best. Now, a core piece of this standard is something called ASIL, the Automotive Safety Integrity Level. It's basically a way of grading risk. You've got ASIL A, which is low risk, like your radio failing, annoying but not dangerous. Then you go all the way up to ASIL D, and that's the highest risk. We're talking failures that could lead to severe or even fatal injuries, like losing control of the truck's powertrain. This functional safety tree here gives us a great real-world example. Now, don't worry that the text on this specific slide isn't in English. The concept is what matters. You can see that basic communication functions might get a rating like ASIL B, but the really critical stuff, like the powertrain control we just mentioned, that gets an ASIL D. And the higher that ASIL rating, the tougher and more rigorous the design and testing requirements. So once you've graded all the risks, what do you do about them? Well, engineers turn to this really powerful tool called a failure mode and effects analysis, or FMEA. The best way to think about it is structured paranoia. It's basically a big brainstorming session where the team's entire job is to imagine everything that could possibly break, figure out what would happen if it did, and then design a way to stop it from ever happening. And this table gives us a fantastic little snapshot of that process. Let's look at that top row, potential failure, an error in torque output. What's the effect? Well, the vehicle could stall or slip. It gets a high-risk priority number of 120. So what's the recommended control? You build in a redundant sensor and torque limiting protection. Or look at the second row. If the high-voltage safety loop fails to disconnect, that's a shock risk. The solution? Dual monitoring and a self-test. The key takeaway here is that for every single risk they identify, there is a specific, engineered solution designed to counter it. Now, designing a safe system on paper is one thing. Proving it actually works in the real, messy world, that is a whole other challenge. So let's move on to the ultimate stress test. This is where the Design Verification Plan and Report, or DVP&R, comes in. You can just think of it as the master test plan. And when I say master, I mean it's a massive document that connects every single feature, every safety requirement to a specific test case, a specific method, and a specific result. Nothing is left to chance. And the process is just incredibly systematic. First, you analyze every single requirement to make sure you can even test it in the first place. Then, you define the strategy. Are you going to test it in a computer simulation, on a lab bench with the real hardware, or out in the actual truck? Then you go execute all those tests. And finally, and this part is crucial, you report and track every single result, especially the failures, until every last one is fixed. And this table right here perfectly shows the power of that traceability. Each requirement is linked directly to a test and its result. Now look closely at requirement FR03, drivetrain mode switching. It was tested and it failed. Now that's not a problem. That's a huge success. The process worked. It caught a bug on the test bench before that truck ever got close to a customer. This is exactly why this kind of meticulous testing is absolutely non-negotiable. And believe me, the testing is exhaustive. They start with pure software simulations. Then they plug the actual SCU hardware into a simulated truck. The controller gets frozen down to -40 Celsius, then it's baked up to 85 Celsius. It's shaken violently to simulate a lifetime of rough roads. It's zapped with electromagnetic energy to make sure it's not affected by interference. It's run continuously for over 1,000 hours. Only after it survived that entire gauntlet does it get to go anywhere near a real vehicle. So we've gotten really deep into the weeds of the architecture, the safety design, and the testing of this one controller. But let's zoom out for a second and talk about why this blueprint matters way beyond just this one truck. After seeing this whole process, from that initial idea all the way to those grueling final tests, what is the most important thing to remember? What's the big takeaway here? It's this. This entire structured process is what allows engineers to take something incredibly complex and transform it into something proven to be reliable. It forces safety to be part of the product's DNA from the very first line of code. It creates a paper trail that links every single decision to a requirement and a test, so there's total accountability. And maybe most importantly, this blueprint for building a brain can be used again and again for any complex system where failure is simply not an option. Because at the end of the day, this meticulous, demanding, and rigorous process, it isn't really just about making a better cement mixer. It's about building the foundation of trust for every autonomous car, every factory robot, and every smart device that we're all going to rely on in the future. This is the blueprint for how we can confidently and, more importantly, safely hand over control to the machines that we create.